Good. Now, does this have any pre-lab questions in it?
Yes. 3 or 4.
Okay. Let's do a little introduction first. What we're going to do in this lab is determine the rate equation, the rate law for a chemical reaction. The reaction is going to be blue, was it blue number 1? Blue number 1. Food color, blue number 1 dye. And in that, we're going to have bleach. And that reaction is going to produce some products. And like always, we don't care what the products are. We just care about the measurement of these values. So we're going to, this is a case where we've got 2 reactants, and the discussion of determining the order of rate laws experimentally only allows us to do 1 at a time. So we need a rate law where the reactant is allowed to vary, but only one of them is allowed to vary. The other one is essentially constant. So the way we do that is we make this constant concentration by making it constant high concentration. That keeps the bleach essentially fixed in concentration. And then we watch the, we use, for concentration here, we actually use absorbance, optical absorbance. So we measure the optical absorbance. At the instant we add bleach, we start the timer. And every so few seconds, I forget how many, 10, 15 seconds maybe. We take a measurement. So we get absorbance against time, right? We get these values here. Every 10 seconds, okay. So you go from 0 and you get 10 seconds and 20 seconds. And you watch that until the value of absorbance gets so low that it's not worth watching anymore. And you take that data and you do things to it. You try to find out what the order is for this factor in our rate law. So our rate law is going to look like this. Rate equals some K times the concentration of the blue dye, which will be absorbance, times the concentration of sodium hypochlorite, and each one is going to have its own order, N and M. Okay. So we're going to do this one first. We'll find out what that order is. So we can do that with 1 experiment. But in order to get a handle on what happens to this one, we're going to change the concentration. We're going to take half the concentration, which is still high enough, and read it again. Do the whole thing over again. Now, because this is set as constant, it's so high that it's constant, then what we're actually doing for this part right here is we're taking this constant and combining it with this one, which is essentially constant. And that's equal to a pseudo rate constant. And that's times absorbance. Again. So we do that for both experiments. All right, so I'm going to stop there and pick it up in a few minutes. Actually, the first thing you do is you find out what concentration of bleach will decolor your blue dye in less than 3 minutes. And once you figure that one out, that's your full strength. So we do a full strength and we do a half strength. So we're going to have a K prime for full strength. I guess I'm going to keep talking anyway. And then we'll have a K prime for half strength. There are two different values because this changed. It's still high enough to be considered constant, but it did change. So we're getting two K prime values. Remember, for this reaction, there's still only one K. So we got to get at that eventually. Okay, so let's go to the pre-lab questions and work on those a little bit. Let's see. Pre-lab. In order to complete this operation over here, eventually we've got to know the molar concentration of sodium hypochlorite in that solution. If we know the full strength, then it's easy. We just take half of that and that's the half strength. So that's what this first equation is about. So a container, household bleach has 5% sodium hypochlorite by weight. What does that mean? 5% sodium hypochlorite, this is aqueous, weight. That means there are 5 grams of sodium hypochlorite for every 100 grams of solution. That's what that means by weight. If the density is 1.08 grams per mil, calculate the molarity. Right? So this is a dimensional analysis problem, actually. We want to end up with a moles per volume. So we can convert moles first if you want. Do that. Grams, moles. So we're going to find out how many moles that represents. So sodium hypochlorite, right? 23. Sodium is 23 grams per mole. Oxygen is 16. And chlorine is 3545. So this should be the molar mass of sodium hypochlorite. So then 14 and 1, 2, 5, 6, 7 grams per mole. 7445. Right. So that converts sodium hypochlorite to moles. Now we need to convert the solution to volume. So that's 100 grams. What's the density of that solution? 1.08 grams per mil. So grams of solution gives us milliliters. 1.08 grams per mil. So that takes that one out. But molarity is per liter, correct? Mm-hmm. Right, so we gotta get rid of the milliliters and leave us with liters. So this is 10 to the third, 1,000 milliliters per liter. So that calculation should give us the molar concentration of sodium hypochlorite in 5% bleach. Let's see. 5 divided by 100 divided by 7445 times 1.08 times 1,000. So I get 0.725 molar. Okay.
How can I do that? Just put 7 points or 0.73. Is that okay?
Well, we got 3 significant figures. I mean, I didn't put them up here. I shouldn't have.
Yeah.
This is 5.00. So we got 3 significant figures. We can keep all 3 of them. Okay. Let's see. That was 1. How about 2? How many grams per liter of sodium chloride are required in order to prepare a solution with a concentration equivalent to the solution in question 1? If this is 0.725 molar sodium hypochlorite, why would we want to determine the concentration, be able to make a solution of sodium chloride?
Dilute it?
Yeah, we want to dilute the bleach. But we can't just dilute the bleach with water. Because there are other factors involved when the bleach gets to acting on things here. What we want is something that has the same ionic strength in solution as sodium hypochlorite, but without the bleaching effect. So if we just take the oxygen out and do sodium chloride at the same molar concentration, then that's our diluent. So when we make our half-strength bleach, we can go full-strength bleach for one experiment, and then half-strength, we add half of it as sodium chloride solution at this concentration, and the other half is the bleach, because that cuts the concentration in half. It's all about the ionic strength. They need to be equal. Okay, so what we want to do is we've got this concentration, 0.725 grams of sodium chloride per mole, per liter, excuse me, not grams, moles. Moles per liter of solution. Okay. Prepare a solution with a concentration equivalent. How many grams per liter? So we've got the volume all right. We just need to convert the moles to grams, right? So we get rid of moles, leave us with grams. We just need the molar mass of, well, all we have to do is drop out the oxygen. One sodium, one chloride, and now the value becomes 5845. Let me see. 7445 minus 16. Yeah, 5845. So 58.45 there. And the moles cancel, leave us with grams per liter, which is the unit of measure we're looking for. 0.725 and 58. Oops. 58.45. So we need 42.4 grams per liter of sodium chloride to give you that. Okay. Now, as far as the experiment goes, we're not using 5% sodium hypochlorite. We're using, I think it's 6.5%. That factors into your calculation later. This is just to show you how we got there. And then I've already calculated how much of this you need to match the experimental bleach concentration. All right, so that solution is already prepared. All right. So what do we got left? Number 3.
Mm-hmm.
What's the percent sodium hypochlorite by weight for a liter of bleach that is 0.8 molar sodium hypochlorite and has a density of 1.09 gram? Okay, this is taking that experiment number 1 and going in reverse. What's the percent by weight? So if we're starting off with 0.8 molar, 0.8 moles of sodium hypochlorite per liter, we want to end up with grams per 100 grams of solution. So we got to change the moles to grams. 75.45, is it?
Mm-hmm.
So it's 75.45 grams per mole. Okay, that takes care of that part. Now we want to reduce that liter to 100. Actually, we want to make milliliters out of it first, don't we? So in order to use the density. So liters, milliliters, that's 10 to the third. That gives us milliliters. That's milliliters of solution. Now we can multiply that times our density factor, but we need, it's grams per milliliter, 1.09 grams per milliliter. So milliliters has to be on the top, grams at the bottom, 1.09 grams per milliliter. That gets rid of the milliliters. Now we got grams. But that's per gram. We want per 100 grams. So we have to use a factor of 100 times that. And that should give us our answer. It's kind of like calculating percent. You know, you always have to multiply times 100. 0.8, 75, 45. 1,000 divide 1.09 divide and 1. So I get 5.54. 5.54, which would be 5.54% sodium hypochlorite by weight. That looks reasonable, right?
It's close to me myself, I got 5.4.
I'm looking at the first one where we had 5%.
Yeah.
And 5%, we got 0.7 something something. 0.8 bumps it up to 5.5. So relatively speaking, we're in the ballpark.
We're in the ballpark.
Yep. Okay. So those are the pre-lab questions. Let's see. Oh, 6%. I think we're using 6% hypochlorite.
We are.
Yeah, 6%. Okay, this rehashes some things about first, second, zero, first, second order. This one talks about the pseudo rate constant. Here we're preparing things. I'm going to prepare, I've already prepared a 0.878 molar sodium chloride, so that's your diluent for your half strength. This experiment was originally set up for a blue number 1 and red number 40. And I'd have, when the class was big enough, I'd have half the class doing blue and half the class doing red. But with our small class size, I just chopped it down to blue. Blue tends to work better anyway. Let's see. And there's your wavelength on your, we're going to use a spectrophotometer to measure the optical density of our solution. And you'll see the value of absorbance going down, 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 down over time at 630 nanometers. So I'll go, when I set the lab up Thursday, I'll come in, I'll turn the spectrophotometer on and set it on 630 and let it be warming up, because they like to be warm when you first use them. And this part of the experiment, you determine how many drops of bleach required to. The thing about this, these steps in the equation is, if you use 5 mils of your diluted dye, and I've already got that prepared too, you don't have to dilute it. 5 mils of diluted dye, and you find out how many drops of bleach is required, full strength bleach, to decolor it in less than 3 minutes. Yep. Then you need to be sure that you keep that pipette dedicated to the bleach delivery, because it delivers a certain size drop and they're not calibrated. So you can't take one and say this one pipette's going to do the same as this one. So once you determine that number of drops, you need to keep that pipette separate and identified as the bleach dropper. The other problem is the little cuvettes, the little square glass cuvettes, actually they're polycarbonate cuvettes that we use in the spectrophotometer, are not 5 mils. The maximum they will hold is 3 mils. So once you find out how many drops per 5 mils, you need to prorate it for 3 mils. Like 3/5 of how many drops gives you the right amount. And then you want to deliver 3 mils of your colored solution into the cuvette. And then you want to get ready, because as soon as that bleach hits that blue, it's going to start decoloring. You want to catch it as close to the beginning as possible. So you want to stick your cuvette into the spectrophotometer and then add the bleach to it. And use a small glass rod and just dip it a couple of times to be sure it's mixed, and then go. And you'll notice that if you're reading the absorbance on the device, it'll start out here, and by the time you get ready to start your timer, it's already dropped 0.2 of a unit. So it goes fast. The only way we could manage it quicker is to tie the spectrophotometer into a data recorder. Then you can get the data from the instant you add the bleach. And I haven't done that. I don't have the funds. I guess I could apply for a Perkins purchase for a data recorder. We do that. Anyway, so you're going to watch it. You're going to record all those absorbances. Now, why do we use absorbance instead of knowing the concentration of blue dye? Convenience. Right? Absorbance is a linear response to concentration. Right? Beer's law. I think I've got a section in there on Beer's law.
Yeah, it's in the post lab questions. It's the first one.
Right.
It says the data in this experiment obeys the Beer-Lambert law, explain this law.
Right. Absorbance is equal to 3 things. I usually write ABC. C is concentration. Right. So as the concentration goes down, the absorbance goes down. Let's see. I forget which one is which. I think B is path length. So the longer the path length, the more absorbance you get, because the light's got to travel through a greater distance of your chemical. And then A is the absorptivity. And that's characteristic of the molecule itself, what we call the chromophore, part of the molecule that absorbs light. Now, we don't have to know this. What this tells us is that A responds linearly to both concentration and path length. Path length is going to be constant. The path length is 1 centimeter, right? So that's not going to change. The absorptivity is the same also. So the only thing that varies is concentration. So we're using absorbance as a measure of concentration. Now you'll see on spectrophotometers, you have 2 ways of reading them. You've got absorbance units and you've got percent transmission. Right? They're not exactly opposite one another. This is an arithmetic progression, like 1, 2, 3, 4, 5. Absorbance is a log function. And the log function is the one that's linear. This one is not linear. That's why we use absorbance. Okay. Let's see, what else do we need to talk about? Anything? I've got some blurbs on calculations at the back. That table has red number 40, but you can ignore that part. Post lab questions, okay. I'll let you do those on your own. Follow-up calculations. This page is on calculating the concentration of bleach. All right. So you're gonna take that dropper. You can do this after the experiment. Take that same dropper and go to the balance and put so many drops in there. You know, more drops is probably better. So in this case, our example of 79 drops gives you 3.9 grams. And we use that plus the density and the concentration of, actually, density. I don't need density, not for this calculation. You just need the concentration, which is 6 grams per 100 grams, and the molar mass. And that will give you the number of moles of sodium hypochlorite that you added for every drop. Okay, so if you add, I don't know, 30 drops to that 3 milliliters, then 30 drops times that value will tell you how many moles of sodium hypochlorite you added to that reaction vessel. Then you need to know what's the volume. Well, you added volume, so it's 3 mils plus something. So that's what we do with the volume of bleach added. Here we can use, actually, there are 2 ways to get that volume per drop. You can either say 4 mils of bleach gives you 79 drops. You take 79 drops into a graduated cylinder and see how many milliliters it is. Or you can take the mass of the bleach that you added and use the density, which I believe is 1.09 for this mixture, and calculate the milliliters per drop. Then you know that if you add 30 drops, it's 30 times that value is plus the 3 milliliters is the total volume. Now you have the moles of bleach, you got the volume of bleach, volume of the container. You can calculate the molarity of the bleach in that solution. That's the full strength molarity. Okay. Once you know the full strength molarity, just take half of it, and that's the half strength molarity. So that's what that page is for, calculating the molarity of the bleach. The subsequent pages are what you do with the data to find out the actual. First, you want to find out the order of your K, order of your blue dye, right? And you do that from your plots, right? You take your data and you plot your raw data. If it's got a curve, like time against concentration, it's not 0 order. Take the natural log. If that's a straight line, it's first order. If that's not it, then you go to second order. You know, the inverse, plot that against time. If that's a straight line, then it's second order. So you're going to do that for both the full strength and half strength experiments. So then you got the order for the blue dye. Now we need to find out the order for the bleach. And that's where we ratio, right? This G right here. We found out the first order. So we know that the K value, the K prime value is extracted from the plot. Once you have the linear plot, then you can find the K prime from the slope of the line. So you need the slope of both of those lines. One of them is the K prime for the full strength, and the other is the K prime for the half strength. Once you know those K primes and what they're equal to, right? The K prime is equal to actual K times the concentration of sodium hypochlorite to the M value. Now, if it's K prime full strength, it'll be simple K plus the full strength. And the K prime for the half strength will be same K, which we don't know right now, and the half strength concentration. So you know those two. You know the full strength, you know the half strength, full, half strength, K prime. You ratio the two, like we did with our experiments in determining. And then you ratio these two, which will be different values. The K's cancel because they're the same value. These values combine to the M power, and you can deduce the M value from that. And once you have the M value, then you can go to, let's see, then you can go to, yeah, once you have this value, then you can take either one of these and say, we know what that is. We know what this is. Now we know what that is. we can solve K. And you find out what the K is. And that K goes into your rate expression. It goes here. You got this one from your earlier plots. You got this one from that calculation. That's your rate law. Okay. So there's a lot of math here, but it's really fairly simple and straightforward. And I think that's the end of the, yeah.